Hello everyone, my name is Çağlar Demir. In this talk, I would like to present a new scalable embedding model for knowledge graphs. This work is done in the DICE research group of Paderborn University by collaborating with Axel and Gonga. We call this new paradigm a physical embedding model for knowledge graphs, in short, PYKE. PYKE attempts to learn embeddings of entities and relations for a given knowledge graph by combining a physical model with an optimization technique inspired by the simulated annealing. Before diving into details, I would like to briefly highlight the significance of knowledge graph embeddings. Knowledge graph embedding methods allow us to leverage many machine learning algorithms on knowledge graphs, as such models do not abide by graph data. By learning embeddings, many machine learning algorithms can be applied to address various inherent problems of graphs, such as type prediction, link prediction, community detection, and many more. But in our work, we mainly focus on the type prediction tasks. As you may very well know, the number and the size of knowledge graphs available on the web grows steadily. As a result of this, utilizing machine learning algorithms on graphs became more attractive than ever. The steady growth in the size of the graphs magnified the importance of the scalability, since many knowledge graph embedding models do not scale well due to their high time and space complexities. This apparent scalability issue led researchers to focus on the asymptotic behavior of models as the size of knowledge graphs grows. The research question of our interest is to devise a scalable method, that learns good embeddings for large knowledge graphs in reasonable time. Within this regard, we propose a new scalable paradigm, PYKE. In our experiments, we show that PYKE goes beyond all computing state-of-art models with respect to its efficiency and effectiveness. As seen on the right-hand side, PYKE requires only 25 minutes on DRUGBank and outperforms all other approaches by a significant margin on the type prediction task. Next, I would like to introduce PYKE in detail. PYKE begins with constructing a similarity matrix based on a similarity function that is predefined over the vocabulary of resources. After the similarity matrix is constructed, we truncated it into positive and negative examples for each vocabulary terms. Thereafter, we map each vocabulary term to its initial embeddings according to a distribution. In our work, we used simply random distribution. As a last step, PYKE starts to iteratively update all embeddings of vocabulary terms by ensuring two important points. First, the embeddings of similar vocabulary terms are close to each other, while embeddings of dissimilar vocabulary terms are distant from each other. Therefore, after the embeddings are learned by PYKE, we expect that in this newly learned vector space, similar vocabulary terms should have small amount of Euclidean distance, while keeping a large Euclidean distance to the dissimilar vocabulary terms. In the next slide, I would like to briefly explain such 4 steps. First, given a knowledge graph shown in the below figure, also we use the same knowledge graph as an example in our paper, we construct a similarity matrix based on we construct a similarity matrix by using pointwise mutual information. One could use any function to capture similarities between vocabulary terms, provided that the range of such function is between 0 and positive infinity. And next, we truncate similarity matrix into positive and negative examples for each vocabulary term to avoid the oversampling problem. For each vocabulary term, we choose k positive and k negative vocabulary terms. As seen on the below figure, for Michel, we choose type and female vocabulary terms as positive examples, provided that, of course, k is greater than 2. And we randomly sample k vocabulary terms as negative examples. In contrary, for Stefan, we use Marcus, male, and Heschild as a positive examples, and we randomly sample any of the vocabulary terms where the entries are zeros. After similarity matrix is constructed and such matrix is truncated, PYKE iteratively updates the embeddings. At each iteration, as you see in the right hand side, vocabulary terms are being pulled and pushed by the positive and negative examples. To model this attractive and repulsive behavior, PYKE employs Hooke's law and its inverse, respectively. As you see on the right hand side, that F subscript A denotes the attractive forces through the positive examples for given vocabulary term. And the similar the vocabulary terms are, the higher the attractiveness, higher the forces between them. While F subscript R denotes the repulsive forces. For a given resource, for a given vocabulary term, we calculate the attractive and repulsive forces through a truncated version of similarity matrix. Thereafter, PYKE dampens attractive and repulsive forces by reducing the total energy in the physical system by a fixed amount of energy. As one can imagine, that at the very beginning, the attractive forces and repulsive forces are very effective, and as the PYKE iteratively updates the embeddings, the amount of energy in the system is decreasing. Therefore, the impact of attractive and repulsive forces are reduced. As you may see in the figure, similar vocabulary terms are indeed close to each other in the projected embedding space, despite the information loss occurred due to principal component analysis. The embeddings of female, type, and Michel have a closer Euclidean distance, while they keep the large Euclidean distance between Heinz, Martin, Anna, and others. The goal of our evaluations was to compare the quality of embeddings generated by PYKE with the state-of-art models, or against the state-of-art models. To this end, we used two evaluation scenarios on benchmark datasets. Those evaluation scenarios are type prediction and cluster purity. In the table below, calligraphic G denotes the number of RDF triples in a graph, in a knowledge graph, and V denotes the number of resources. Calligraphic S denotes the set of all unique resources having several type informations, and calligraphic C denotes the set of unique classes in knowledge graph. For instance, resource of Barack Obama should have several type informations, as Barack Obama is a person, a politician, and as well as a president. Therefore, Barack Obama has several type informations, and we would like to capture this information by S, calligraphic S. To evaluate type prediction performances of models, we applied nearest neighbor algorithm to find new nearest neighbors of each unique resources having several types. Thereafter, we map each resources into a binary type vector of length C, where the eth entry of a binary type vector is 1, if and only if given resource has the respective type, otherwise 0. For instance, as we previously mentioned, Barack Obama has the type information of a person, politician, and president. Therefore, the respective entries in the binary vector is 1. They are 1, while type information of car or country will be 0 for the Barack Obama. We reported the average of the cosine similarities between type vectors of each resources and its mu nearest neighbors. As you see on the right hand side, that we choose various number of nearest neighbors for each resource, starting from 1 to 100. And the plots show that PYKE significantly outperforms the old state-of-art algorithms on both benchmark datasets. If we take a look at a little bit deeply, we see that the learning on drug bank above plot, it is easier than learning a good embeddings and on Wikipedia. We believe that if you look at the previous slide, we believe that this difference resulted because of the size as well as the number of unique classes. Where the drug bank has 102, Wikipedia has 423 class informations. To perform the cluster purity, we applied HTB scan clustering algorithm, which is a scalable approximation of DB scan. The hyperparameters of HTB scan are fixed throughout the experiments. We calculated the purity of a cluster as shown in the left-hand side. A high purity means that the resources with similar binary type vectors are located close to each other in the embedding space. And PYKE also outperforms all computing approaches on both benchmark datasets. We were also interested in determining the asymptotic runtime behavior of PYKE on large knowledge graphs. To this end, we conducted runtime experiments by using 4 synthetic benchmark knowledge graph datasets. As figure shown that PYKE scales close to linear in the size of knowledge graph. Our results show that PYKE is an effective and efficient knowledge graph embedding model and opened various other research avenues. In our future work, we would like to explore other similarity means based on the local similarity metrics, local similarity means. And we would like to explore a better initialization technique for embeddings so that we could achieve a faster convergence. Thank you for your attention. If you have a question, please do not hesitate to write me an email or tweet to me or write a Twitter on Twitter. Thank you.